Hello, friends. So, welcome to the class. Here, we'll discuss more problem on quantum mechanics. So, here basically we'll discuss about the application of quantum mechanics for CSIR NET examination or GATE examination or any other competitive examination like JS, TIFR, BARC. So, welcome to the class, all of you. And first topic here we'll discuss about step by step we are taking the topic linear harmonic oscillator. Linear harmonic oscillator. So all of you know, friends, that whenever we talk about a system, quantum mechanical system, always some parameter must be given, some information must be given. So that parameter is called your potential. If the potential of any system is given, you can describe the behavior of the potential system. You can describe the characteristics of the system. Everything can be discussed depending on the potential, because by knowing the potential one can identify the system also. So in CSIR or any competitive examination, they will give you the potential. Sometimes may not be the harmonic, they may not mention the harmonic oscillator, only will give the potential. So but just knowing the format, just looking the format of the potential, you can identify the problem. So maybe the problem, suppose Vx equal to potential is given, Vx equal to half of m omega square and x square, and the limit of x is suppose minus infinity less than x less than plus infinity. That means x lies between minus infinity to plus infinity. So all of you know that this potential is nothing but the potential of a harmonic oscillator. Potential of a harmonic oscillator. So if you try to solve this problem, there are very many methods are there. If I mention the methods here, one method is called analytical method. Analytical method. And second method will be operational or algebraic operator method. And third method, another important method, it is also important for slowly, but potential is very slowly varying potential, so that is called WKB approximation method. So using the three methods, so one can find the same solution. But here you see, in analytical method, what we do basically, we take the Schrodinger equation and we put the values of potential here, Schrodinger equation, and we got an asymptotic solution, and that means the energy eigenvalue and the wave function for a various state. In operator method also we take the A dagger, x cap, those operator. So you can take, so using the, you know already in your semester in class, that this operator method also can be used for solving the Schrodinger harmonic oscillator. Another WKB approximation, but just by putting the condition of WKB approximation we can solve. But we are not going into how to solve this analytically algebraic operator method or a WKB method. So if you want, so I can give you the detailed solution, but since our discussion is based on application of this harmonic oscillator, and it is not like that. So if you know this, how to solve it, operator using operator analytical or WKB, that is not enough, because there will be a different kind of problem in CSIR examination. Never they will never ask you, okay, solve it analytically, operator or WKB method. So they will give you some different question related to harmonic oscillator, and you have to solve. So on those topic we will discuss here. So suppose friends, this harmonic oscillator is given. So if I say that all of you are knowing that when this problem is given, so simultaneously we have to look at the potential and you have to look at the ranges of potential, this x, so limit of x. So I can say so that when this type of potential is given, instantly we can write the energy eigen value, that is En equal to n plus half a squared omega, where n starts from 0 1 2 3 4 dot dot dot. So this n, putting n equal to 0, will get ground state energy, that is also called 0 point energy. And if I take n equal to 1, then first excited state n equal to 2, second excited state n equal to 3, third excited state, and so on. And correspondingly, the wave function one can find psi nx. Okay, psi nx, or psi nx equal to one normalization constant. So I'm just putting the normalization constant, and another function, that is polynomial, we can write is nx. This is called Hermite polynomial. And another factor will come e to the power minus m omega x square upon 2a squared. Okay, so this normalization constant one can find by using the normalization condition. Okay, and this Hermite polynomial, one has to know that different values of Hermite polynomial, suppose a is 0x, a is 1x, a is 2x, those values. So I have written in this format so that it is very easily to calculate and the wave function of different states. So you see, this is the harmonic oscillator here is given in one dimensional. Okay, so in 1D, if it is 1D potential, then I can directly write like this. Clear? Now see, when the potential is given in 2-dimensional, what will happen? Or when the potential is given in 3-dimension, then what will happen? Clear? So for 2D potential and for 3D potential, what are the energy eigenvalues, different wave functions, and what are the degeneracies of different type of different energy level, and what type of degeneracies are occurring? So those we will discuss here. Clear? Now see, if I say that this, okay, let us take the one energy eigenvalue. So suppose if I take n equal to 0, it will be E0, and it will be, if I put n equal to 0, half a squared omega. So this is ground state energy. This is ground state energy. Clear? If I take n equal to 1, you will get E1 equal to 1 plus half equal to 3 by 2 a squared omega. So this is called first excited state energy. Similarly, if I take n equal to 2, E2 equal to 2 plus half is 5 by 2 a squared omega, second excited state energy, and so on, one can find out. And what will be the wave function for different state? If I take n equal to 0, that means for ground state, psi 0x equal to that normalization constant I am writing here, or let us take it n naught. Since n equal to 0, so I am taking, suppose, n naught, the normalization constant. A is not x, and e to the power minus m omega x square upon 2a squared. So further, if you solve it, n naught, so h0x, what is the value of h0x? That is 1. Okay, that means Hermite polynomial, by using Rodriguez formula you can find out. So e to the power minus m omega x square upon 2a squared. So in this way, one can find the solution, normalization constant e to the power minus m omega x square upon 2a squared. Clear? So for finding the normalization constant, you can take the condition of normalization. So if you are getting stuck, if you are stacking somewhere, then let us take the normalization as, just I am taking one problem one wave function. Rest of the thing you can do, but our main target, I mentioned, that degeneracy dose. So let us help this thing, normalization. So for normalization, since the limit is given here minus infinity to plus infinity, so I will take that minus infinity to plus infinity psi naught, minus infinity to your plus infinity, and psi naught x and psi naught star x dx, and that normalization condition, this must be 1. Clear? So if I put psi naught x or psi naught x star x, so one normalization constant will n naught square, so I'm putting n naught square here. So minus infinity to plus infinity, and e to the power, it will be minus m omega x square upon a square, because 2 factor will come, this 2 factor and this 2 factor will cancel each other. So and dx. Okay, so this is an standard equation. It is a standard equation. Although if since this integration, you know that minus infinity to plus infinity to e to the power, suppose minus alpha x squared dx, so this value is basically under root pi upon alpha. So here alpha, if you compare this, alpha will be your m omega upon a squared. Okay, so m omega upon a square, so directly one can find out n naught square, and so this value will be under root of pi a square upon m omega, and that is equal to 1. So from this the n naught value will come, so n naught equal to it will be your m omega upon pi a square to the power 1 upon 4. So therefore psi naught one can find out, psi naught x is equal to m omega upon pi a square to the power 1 upon 4 e to the power, and e to the power minus m omega x square upon 2a square. So this is the final wave function for ground state. Similarly, one can find out the wave function for first excited state, second excited state, by using the normalization condition. So you see, whenever you discuss any kind of problem, so any energy level, so then what will be the degeneracy of that energy level? See, if I say the ground state energy level, it is a ground state energy level. So how many wave functions are there corresponding to this ground state energy? So only wave function. So degeneracy, you can say it is non-degenerate, or degeneracy is 1. So similarly, for this state you will get only one wave function, for this energy level you will get only one wave function. That means in 1D harmonic oscillator, all energy levels are singly degenerate. All energy levels have the degeneracy only one fold degeneracy, or you can sometimes say the non-degenerate case, or degeneracy is 1. So this is the problem that we discussed here. Now let us move to the 2D or 3D potential. So let us first move to the 2D potential. So in 2D, this is suppose 2D harmonic oscillator. Clear? 2D harmonic oscillator. So in 2D harmonic oscillator means two-dimensional harmonic oscillator. That means the oscillation will be in two direction. So earlier it was 1D potential, the vibration or the oscillation was in only x direction. So here 2D means the oscillation will be in two direction. So the potential, suppose I am taking Vxy, so here variable is x and y, that means the oscillation potential will be along x axis or along y axis both. So that is equal to, suppose, Vx plus the total potential Vy. Clear? Vx plus Vy. So this is 2D potential. So the corresponding energy eigenvalue, what will be the corresponding energy eigenvalue? So your E, I will write it E nx and ny. That means nx means the energy along x for Vx, and Ny means energy for Vy. Okay, so the total energy will be, if the potential are additive, that the total energy will also be additive. So Enx plus Eny. Okay, and the eigenfunction, this is the energy, this is the energy, and the eigenfunction or wave function, eigenfunction is multiplicative. So when it is a multiplicative, so I will say psi nx and ny will be a function of what, x and y. Okay, and this will be psi nx is a function of x and psi ny is a function of y, since wave function is multiplicative. So this we have mentioned here. Similarly, in 3D, what will happen? In 3D harmonic oscillator, that potential will be given in x, y, z variable, Vx plus Vy plus Vz. What will be the energy? Energy will be your Enx, Ny, Nz. That will be the, for Vx it will be the Enx plus Eny plus, this is for Vy, and for Vz Enz. What will be the wave function is multiplicative, or wave function or eigenfunction same. This will be psi nx and y and z, and it will be a function of what, all the three variables will be present, x, y, z. That will be the, since it is multiplicative, psi nx is a function of x, and psi ny is a function of y, and psi nz is a function of z. So this format we have known that when 2D is given, then the energy will be just additive, the wave function will be multiplicative in this way. Now we'll move to a problem for 2D harmonic oscillator. So you can pause it and you can write it down. So let us take an example for 2D harmonic oscillator. Clear? Suppose in your examination the potential is given like this: Vxy equal to half of m omega x square, m omega x square plus y square. Okay, and see, the potential must be given as well as the ranges of potential should be given. So it is suppose minus infinity less than x, y less than plus infinity, suppose. Okay, so this is a 2D harmonic oscillator. How can you say that 2D harmonic oscillator? This will be the half m omega square x square plus, I can, if I multiply it, half m omega square y square. So this is nothing but your Vx, this is nothing but your Vy. Okay, so 2D. So when that in 2D potential, so one important point is, in 2D potential, when the frequencies along y-axis or x-axis or y-axis are same, here you see, you can see that it is the omega is the frequency and omega is the frequency, and both are same in x-axis, x direction or y direction. When the frequencies are same along all direction, so here we are taking only two direction, then those type of harmonic oscillators are called isotropic harmonic oscillator. Okay, so further you can mention here it is 2D isotropic linear harmonic oscillator. Clear? So 2D harmonic oscillator. 2D harmonic oscillator or isotropic means you can choose any direction. So if you go in x direction or y direction, the same characteristics you will get. So it is 2D isotropic harmonic oscillator. When the frequencies are not matching, suppose here the frequencies is omega, omega 1, here suppose frequencies is omega 2, then frequency omega, if omega 1 and omega 2 are not same, those type of harmonic oscillator will go anisotropic harmonic oscillator. So that we will discuss later. So let us first discuss this isotropic linear harmonic oscillator. So instantly I can write the energy eigenvalue nx and ny. It will be, so for Vx it will be, we know that earlier case that 1D harmonic oscillator nx plus half h cut omega plus, so earlier I mentioned it is n only. So here he, since to distinguish n, because n two times will come, so one is nx and another is suppose ny, n suffix y, ny plus half h cut omega. In both the cases frequencies are same. This is our format. Now if I further simplify it, nx plus ny plus half will be 1, that will be your h cut omega. Clear? Or I can write n plus half h cut omega, but here n equal to nx plus ny. So this is an important relation to find out the degeneracy of different energy level. Here in all cases n, nx and ny, all values will be started from 0, 1, 2, 3, dot dot dot. That means for n equal to 0 I will get 0 point energy or ground state. For n equal to 1 I will get first excited state. For n equal to 2 I will get second excited state, and so on. Now see, for finding the ground state energy, so let us find the ground state energy. What will happen? So E00, for finding the ground state energy, n equal to 0. So when n equal to 0, nx and ny must be 0, because they all also have values 0, 1, 2, 3. That means nx and ny both equal to 0. So I can write E00, E00, that is equal to, if I put nx and ny equal to 0, it will be h cut omega, or simply n equal to 0, you will get this will be the 1. This will be 1. So you will get h cut omega, only h cut omega. Clear? So for first excited state energy, so this is called ground state energy. Ground state energy. And we'll get first excited state energy. First excited state energy means what will be the value of n, so that the n value will be 1. So n value will be 1. So if I say, if I simply draw a table here, so this is suppose n, this is suppose nx, and this is suppose ny. So when n equal to 0, so we must put nx equal to 0 and y equal to 0. When n equal to 1, we must put, to satisfy this using this relation, either we can put 1 or 0, or either we can put 0 or 1. So that means both the values are possible to get n equal to 1 using this relation. Now, so this value, if I say n E10, that means nx equal to 1 and y equal to 0, so it will be E10. So I can put here n1, nx1 or 0, or simply here you put n equal to 1, so you will get 2 h cut omega. Or simply in this combination E01 also, if we put these two value, or simply n equal to 1, you get 2 h cut omega, but both the values are same. So this is called first excited state. First excited state energy. Clear? First excited state energy. Okay. Now you see, what will be the second excited state energy? Second excited state energy means n equal to 2. N equal to 2. So when n equal to, I write 2, how many combinations will be there for nx, or different values of nx and ny? I can write 2 plus 0, or 0 plus 2, or 1 or 1. This all values are possible. 3 combinations will be there. or I can write simply E02, so or E20, let us take E20 step by step, E20. So nx equal to 2, ny equal to 0, or simply you put n equal to 2, you will get 3 a squared omega. So or E02, again you will get 3 a squared omega, or E11, that means so nx and ny both are 1, both you are putting 1, or n equal to 2, so you will get 3 a squared omega. All the three eigenvalues are same. This is called second excited state energy. Clear? Further, if you want to find out for nth state of 5, 5th excited state, 6th excited state, just you put here and find a different combination. All the energy eigenvalues for a certain level will be same. Now our target is to find out the degeneracy of different energy levels. So what will be the degeneracy of different energy levels? So for that we have to find out the wave functions corresponding to the different energy level. So let us take the first case, ground state energy level. So what will be the degeneracy? So for ground state it will be psi 0 0, and will be a function of x and y. So if I separate it, so psi 0 it will be your psi 0 x, it will be your psi 0 will be a function of x, and psi 0 will be function of y. Now earlier case we know that the wave function, so we got the wave function, so what, and pi so what was the wave functions? Okay, so I'm not normalizing it, just I'm writing the normalization constant here. Okay, so for our simplification, suppose let us take this is n naught, one Hermite polynomial h naught x, and it will be e to the power minus m omega x square upon 2a squared. So this is the wave function for psi 0 x. For psi 0 y it will be again n naught, and a0 will be a function of y, and e to the power minus m omega x square y square upon 2a squared. Clear? N naught and n naught, I can write n naught square. So what will be the value of h naught x, a Hermite polynomial? This is 1. So h naught y, Hermite polynomial, so 1. So it is 1, and e to the power minus, if I combinedly write it, m omega divided by 2a squared, it will be x square plus y square. Clear? So this is the wave function. So this wave functions, only one wave functions we are getting for the combination for the energy, ground state energy. So what will be the degeneracy? So therefore degeneracy for this level, degeneracy for ground state is equal to 1, or singly degenerate, or you can say singly degenerate, or singly degenerate. Clear? Now so we'll try to find out the degeneracy for a fast excited state. So for fast excited state, the combination is E10 and E01. For 10 combination, it will be psi 10, psi 10 will be function of x and y. Okay, so if I split it, psi 1 x and psi 0 y, psi 0 y. So what will be the value of psi 1 x? Your psi 1 x will be one normalization constant will come, that is suppose n1 I am taking, and it is h1 x and e to the power minus m omega x square upon 2a squared. For psi 0 y, so I am taking the normalization constant n naught, and h0 h naught y is a function of y, and e to the power minus m omega y square upon 2a squared. So n naught and n1 and n naught, these are the normalization constant. So n1 n naught, n1 n naught. Clear? So this normalization constant or h1x, what will be the value of h1x, Hermite polynomial, that is 2x. Okay, and h0y is 1, so simply 1 here. So if I combinedly write these two factors, m omega upon 2a squared. So this will be the x square plus y square. So this is your one combination, one wave function. So you can, if you solve it further by using normalization constants, you will have that this value, this normalization constant. So okay, that is not our aim, target. Our target is to find out the degeneracy. And another combination was there, psi 0 1. Clear? Psi 0 1. So psi 0 1 x and y. So if I split it, psi 0 x and psi 1, this will be y. So for psi 0 x n naught is not x e to the power minus m omega x square upon 2a squared. For psi 1, so I am writing normalization constant n1 is 1 y e to the power minus m omega y square upon 2a squared. So n1, n0 and n1 normalization constant, psi 0 x equal to 1 and sorry, a0 x equal to 1 and a1 y equal to 2y will be 2y. So this will be 2y and it is 1 multiplied here. So and combinedly this two factor m omega x square plus y square upon 2a squared. Now see, corresponding these two wave function are similar or different. This factor e raised to the power factor is same. Clear? n0 n1 n0 n1 2, these constant are same, but because of the distinct x and y, these two x and y are different, so these two wave functions are different. Clear? So these two wave functions are different, but corresponding to these two wave function, the energy eigenvalue E01 is equal to E10, we got 2a squared omega. Clear? Okay, so 2a squared omega, and the wave functions are different. So your degeneracy means corresponding to a certain energy eigenvalue, the number of different eigenfunctions is called the degeneracy of that certain energy eigen level. Okay, so following this rule, so we can say that the degeneracy, therefore degeneracy is equal to 2 or doubly degenerate. Doubly degenerate. Clear? Now you see, then we got the degeneracies too. Now I mentioned earlier that what type of degeneracies are there. Okay, so basically the degeneracy is two type. Degeneracy is two type. One is your exchanged degeneracy. Another is called your accidental degeneration. Now exchanged degeneracy and accidental degeneracy is what? So now when we say exchange degeneracy, it means that if we are getting the degeneracy is 2 or 3, suppose degeneracy is 2 I am getting, and if the values are just exchanging between the one particular value is exchanging between the two wave functions, then we will say it is exchange degeneracy. Simply you see here what we got is 1x, is not it? Is 1x and is not y. Clear? And is not x and is 1 y. But you see is 1x, this value is 2x, and here we are getting 1. Here we are getting 1, here we are getting 2y. Clear? So this is just what is exchanged between these four factors. In this it was 2x and 1, and here it is 1 coming and 2x is here. Just 1 and 2x or 1 and 2x or 2y, it is just exchanging between these two wave functions. Are you getting my point? So just 1 and 2x and 2xy, this is exchanging between these two factors, between these two wave functions. Clear? So this type of degeneracy is called exchange degeneracy. and when it is not exchanging it, 1 and 2x, 1 and 2i, when it is not exchanging, those type of degeneracy will call accidental degeneracy. So here you are getting the degeneracy. What type of degeneracy is here? Exchange degeneracy, and it is doubly degenerate or degeneracy is 2. So further will it will be clear for in later case. So this is about first excited state energy. What about second excited state energy? We got the second excited state energy. So how three combinations we got? One is called psi 0, psi 20, and psi 0 to x and y. You see here, psi, if I split it, psi 2x, it will be psi 0 y. Okay, psi 2x, say 0 y. So what will be the value of psi 2x? Can somebody tell me psi 2x? What will be the value of psi 2x? Psi 2x is one normalization constant will come, n2 suppose, and h2x will come here, and e to the power minus m omega x square upon 2h cut. What about the value of psi 0? It will be n naught h naught y e raised to the power minus m omega y square upon 2h cut. Clear? So I'm writing here n2 and n naught. Psi 2x, what will be the value of psi 2x? This value is 2, 1 minus 2 x square. So it is 2, 1 minus 2 x square. This is the value for Hermite polynomial. You can check it also. E to e raised, and what will be the value of h naught y? This is 1. So the two factors here. Combinedly I am writing m omega upon 2h cut, that is h x square plus y square. So this is one. Another combination is, further you can simplify, just I am keeping it here. 0 to case, it will be psi x and y. So psi 0x and psi 2y. So this is n naught h naught x e raised to the power minus m omega x square upon 2h cut, and for psi 2 n2 h to y and e raised to the power minus m omega y square upon 2h cut. So this value will be n naught and n2. This h naught x is 1 and h to y is it will be similarly for 1 minus 2y square, and the other factors are e to the power minus m omega by 2h cut. So x square plus y square. Clear? So this is another wave functions we have got, and another combinations also we can have for this wave functions, that is called psi 1 x and y. Clear? So if I split it, psi 1 x and psi 1 y. Clear? For psi 1 x it will be n1 h1 x e to the power minus m omega x square upon 2h cut. For psi 1 y, again n1 h1 y e to the power minus m omega y square upon 2h cut. Okay, so this n1 and n1 I am keeping it same, and h1x equal to 2x, so h1y equal to 2y. So the other factors are remain same, m omega divided by 2h cut x square plus y square. Now if I compare this wave function, see in all three possible cases these factors are same. Difference is 2x 2y or normalization constant. So in this case this is different wave function, and similarly also this is a different wave function, and this is a different wave function, but corresponding to this all wave functions we have got the energy eigenvalue E02 equal to E20 is equal to E11. We got 3 h cut omega. Is it 3 h cut omega? So for corresponding to this energy level, we are getting three different wave functions. So the degeneracy is, so therefore the degeneracy is equal to what? 3 here. Clear? Now see, for ground state we are getting, so if I just summarize it, for ground state, degeneracy we are getting 1. For first excited state, degeneracy we got 2. For second excited state, degeneracy we got 3. So can you just see the procedure? For ground state is 1, for first excited state 2, second excited state 3, what will be the third excited state? 4, fourth excited state, that will be 5th. That means for nth excited state, therefore for nth excited state, degeneracy is equal to what I can write? N plus 1, where n is equal to 0, 1, 2, 3 dot dot dot. 0 means ground state, so we'll get degeneracy 1, so we verified. So for 1 means first excited state, so you put 1 here, you will get degeneracy 2. For 2 means second excited state, okay, n equal to 2 means second excited state, you put here, you will get 3. So in this way one can find out. So this is a simple case, simple, I mean very simplest formula, but my dear students, this formula is applicable whenever we discuss the isotropic linear harmonic oscillator. Clear? Otherwise, if you want to find out the degeneracy of any energy level, so you must go in this way. So we got into the n equal to nx plus ny. Clear? So 0, that is 0 plus 0, or 1 plus 0, 0 plus 1, and so for second excited state energy 2 plus 0, 0 plus 2, or 1 plus 1. So here degeneracy is 1, here degeneracy is 2, here degeneracy is 3. So this is a general idea, general formula for any kind of harmonic oscillator, but this formula is valid only for isotropic linear harmonic oscillator. This is applicable both for isotropic and anisotropic cases. Clear? So these two, I hope these two procedures are clear to you. So this is the cases. Now we'll move to the 3D harmonic oscillator. Clear? Then we'll discuss if the frequencies are not same, what will happen. So let's move to the 3D harmonic oscillator. So 3D, I'll say isotropic. 3D isotropic harmonic oscillator. Isotropic means in all 3 dimensions we will take the frequencies are same. So suppose your Vx, y, z is equal to half of m omega square x square plus y square plus z square, as well as the limit is minus infinity x, y, z less than plus infinity. That means all 3 values are lying in the same limit. So here you see, you can prove it. M omega square x square plus half of m omega square y square plus half of m omega square z square. So this is nothing but Vx plus your Vy plus your Vz. Clear? Vz. Now instantly the energy eigenvalue nx, ny and nz will be your nx enx plus eny plus enz. So enx, what will be the, that means for Vx equal the energy eigenvalue nx plus half a squared omega, frequencies are same, plus ny plus half a squared omega plus nz plus half a squared omega. So if I further simplify it, it will be nx plus ny plus nz, and half plus half plus half, it is 3 by 2, and that is a squared omega, or further n plus 3 upon 2 a squared omega, where your n is equal to nx plus ny plus nz. So this is an important relation where all the values n, nx, ny, nz, n, nx, ny, nz will equal to, will start from 0, 1, 2, 3, dot dot dot. So for first excited state, so I will have to put that nx, ny and nz all values are simultaneously 0, clear, or n equal to, simply n equal to 0, that ground state, for ground state energy level. For first excited state, I will have to put n equal to 1, and we will see the rest combination. Similarly the other cases. So let us take the ground state energy. So nx or n, y and z both will be 0, then we will get n equal to 0, clear. So you just put nx, ny and nz equal to 0, or simply you put here n equal to 0. It will be 3 by 2 a squared omega, clear. So this is what? This is a ground state energy. This is ground state energy, clear. And for first excited state, so I can write C. So if I make the table, here, n equal to nx plus ny plus nz. For first excited state, we put 0 plus 0 plus 0. For for ground state, we put 0 plus 0 plus 0. For first excited state, we can have 1 plus 0 plus 0, or we can have 0 plus 1 plus 0, or we can have 0 plus 0 plus 1. So these three combinations are possible to get 1 using this relation. Now, so let us take the first case, 1 0 0, this combination. So, or for simply put n equal to 1 or nx equal to 1, and rest of the n, y and z put equal to 0, you will get, so 1 plus 3 by 2, that is 5 by 2 a squared omega. So this is called first excited state energy. Similarly, E010, again you will get 5 by 2 a squared omega, and E001, again we will get 5 by 2 a squared omega. These all values are same, so this is first excited state energy, clear. Similarly, we can find out the second excited state energy. For second excited state energy, I have to take n equal to 2, isn't it? So how many combinations will be there? I can write 2 plus 0 plus 0, or 0 plus 2 plus 0, or 0 plus 0 plus 2, or I can write what? 1 plus 1 plus 0, clear. That means nx and ny both values are 1, and nz equal to 2, nz equal to 0, and 1 plus 0 plus 1, or 0 plus 1 plus 1. So again these three combinations can be happen. So here for second excited state, in all cases the energy eigenvalues will be same. So let us take E200, simply we put n equal to 2, you will get 7 by 2 a squared omega. Similarly, for E020 is equal to E002 is equal to E110 is equal to E101 is equal to E011. You will get 7 by 2 a squared omega. So these are called second excited state energy. Second excited state energy. Clear? So, but to find out the degeneracy, one has to find also the wave function corresponding to the different energy level for ground state energy level, for first excited state, for second excited state. So we will see that for ground state energy level, the wave functions, there will be only one wave function, so degeneracy is 1. But for this first excited state, although the energy eigenvalues are same, but their wave functions will be different. So I will just solve this thing, second excited state, you can solve as your homework. So let us move to this all combination, whether the energy eigenfunctions are similar or different. Then we can say the degeneracy of that energy level. So for the combination, suppose psi 1 for combination 1 0 0 0 1 0 and 0 0 1. For combination 1 0 0, this will be the function of x, y and z. So if I split it, psi 1 similar cases, x and psi 0, it will be a function of y, and psi 0 will be a function of z. Clear? Now what will be the value of psi 1x? One normalization constant h1 n1 h1 x and e to the power minus m omega x square upon 2 a squared. For psi 0, normalization constant, suppose n naught is not x e to the power minus m omega. This is a function of y square upon 2 a squared. For psi 0 z, so normalization constant n naught is not z, and the rest thing is e to the power minus m omega z square upon 2 a squared. Now what will be the value of n, n1, n0, I'm keeping it same. So h1x means 2x, clear, and h0x means 1, and this is a y, okay, this is y, h0 y is 1, h0 z is 1. So the these three parameters I can write m omega upon 2 a squared x square plus y square plus z square. Similarly, psi 0 1 0 x y z, so I can split it psi 0 x and psi 1 y and psi 0 z. Clear? So for this n naught is not x e to the power minus m omega x square upon 2 a squared. For psi 1 y and 1 e to the is 1 is a function of y e to the power minus m omega y square upon 2 a squared. For psi 0 z, it will be n naught is 0 z e to the power minus m omega z square upon 2 a squared. So this will be the n naught and then n1 again n naught. So psi 0x means 1, a0x means 1, a1 y means 2y, this is again 1. So this will be 2y, and the rest of the thing e to the power minus m omega upon 2a squared. So x square plus y square plus z square. For the combination psi 0 0 1 x y z is equal to psi 0 x psi 0 y and psi 1 y. Always you try to write in this way, in this this is z, in this format, otherwise sometime x and y you will get confused. So sometime you will write in place of x, you will write z or a y, so that will make later a big issue. So try to remove those common mistakes. Please try to write like this. So for psi 0 x will be n naught psi 0 is 0 x e to the power minus m omega x square upon 2 a squared. n naught h naught y e to the power minus m omega y square upon 2h cut for psi 1 x n1 psi 1 z means n1 is 1 z and e to the power minus m omega z square upon 2h cut. So n naught here, from here n naught and this n1, clear. H naught x is 1, h naught y is 1, h1 z is 2z, clear. And the rest are the things that remain, e to the power minus m omega upon 2h cut x square plus y square plus z square. Now you see this e raised to the power factor, this e raised to the power factors are same. Different is here it is present z and y present and x present. These are all different, so that the wave functions are different. These three wave functions are different, but corresponding to these three wave functions, the energy eigenvalue E001, that is E100 plus E01, E010, that is we got what 5, we got the eigenvalue, energy eigenvalue 5 by 2 h cut omega. So what will be the degeneracy? Corresponding to the same energy eigenvalue, we are getting three different eigenstates. So therefore the degeneracy, is equal to 3. Clear? Now similarly we can find out the second excited state and fourth excited state, nth excited state. Clear? Now if I compactly write it, that for ground state energy, the degeneracy we got 1, clear. And for first excited state, we are getting degeneracy is 3. Now what will be the degeneracy for second excited state? See, degeneracy here I can say that how many combinations we got for this level, for this second excited state energy, 1 2 3 4 5 6. In this combinations, the energy eigenvalue although the same in all cases, but in these combinations the wave functions will be different. In these combinations wave functions will be different. In this combination all the three combinations wave functions will be different. You see how it will be different. Okay, when I take 2 0 0 combination, h2x will be present here h2y present, and here h2z will be present. All the threes are different. Here h1x and h1y will be present. Here h1x and h1z will be present, the Hermite polynomials. And here h1y and h1z will be the Hermite polynomial, because all the Hermite polynomials have different values, so that all the wave functions will be different. So for second excited state we will get the degeneracy 6 here. So for second excited state energy, the degeneracy will be 6. Can I write in a very compact form? So for nth excited state, similarly is in this way. So for nth excited state, degeneracy I can write n plus 1 and n plus 2 divided by 2. Let us check it. When n starts here, all these cases n will start from 0 1 2 3. So when n equal to 0, so this will be the 1, this will be 2, 1 into 2 2 cancel each other, this will be 1. Verified. When n equal to 1 first excited state, n equal to 1 means here I will get 2, here I will get 3. 2 3s are 6, 6 divided by 2 is 3. It is verified. When n equal to second excited state energy, for n equal to 2, here we will get 3, here we will get 4. So 3 4s are 12, 12 divided by 2 is 6. So similarly nth excited state, for nth excited state, this will be the your degeneracy formula, but please remember that this formula is valid only for isotropic isotropic cases. That means when the frequencies are same. But our general way is what? General way is, if we know this relation and just put in this way, and you see how many combinations for a particular for a certain energy levels have, that number of combinations will be the degeneracy of that certain level. So this is the general way, and that one our compact very simplest form. So I hope you got the idea that how the harmonic oscillator, if the harmonic oscillator is given and if it is isotropic, then what will be the degeneracy, what are the different energy eigenfunction, what are the different wave function, and how to normalize it, and what are the degeneracies, and what type of degeneracy, whether exchange or accidental. This all parameters, all things are, I hope it is clear to all of you. So in next class what we'll discuss the anisotropic case. When anisotropic, that means when the frequencies along the different directions are different, then those cases will be called as the anisotropic cases. And sometimes the ranges of potential may be different, clear, or sometimes the ranges of potential different, or in harmonic oscillator, suppose 1D potential is given, harmonic oscillator potential, another 1D potential given combinedly, then what will happen? Clear? So those kind of things we will discuss in the next video, in the next class. So if you think that this is a very helpful to you, so please share it. So please share my YouTube channel, that is just simply type easy physics / Atowar Rahman, and please do subscribe and like it and share it to all your friends, so that they can also get help from my a small initiative. So thanks to all of you.